Okay. So the most important thing is the exam on Thursday. So exam 1 is Thursday. We've been doing 2D kinematics for a little while, but none of the 2D kinematic stuff is going to be on the test. So the topics for the test are only up through vectors. Just if you look at the daily problem sets, there's units in scientific notation, 1D kinematics, and then there's vectors, and then there's 2D kinematics. None of the 2D kinematics kind of stuff will be on it, only up through the vectors stuff. Okay? So up through vectors. So what does that mean? You need to be able to calculate vector components in a coordinate system. You need to be able to, once you calculate the components of vectors in a coordinate system, you need to be able to add vectors, multiply vectors by numbers, and give the components for those. So remember doing all those kind of problems. So yeah, any kinematics is going to be one-dimensional, just along a line. Be ready for some unit type stuff, and that's it. Anybody have any questions about the test? Yeah.
For the 1D kinematics, are the equations to be given?
Oh yeah, every equation that you need is going to be given all semester. And for unit conversions and prefixes and stuff, all that kind of stuff will be given too if you need it. Okay. I won't give steps for converting scientific notation, but I'm not planning to emphasize that anyways, but you should know how to do the scientific notation stuff on your own. There probably will be at least one question where I ask you to give your answer in scientific notation. I don't like to put that stuff on the test too much because half the class has calculators that just do it all for you, so it doesn't seem super fair. So any other questions? Okay. Any homework questions anybody has? I'd be happy to go over homework questions for stuff that's relevant for the test or anything like that. Okay. So remember last time I talked about the second, what do I call it? Yes, thank you. The second common misconception. And that is that the horizontal motion of an object, like people tend to think that the horizontal motion of an object affects how gravity acts on the object. And we saw that that wasn't true. If you fire a bullet horizontally, it still hits the ground at exactly the same time as if you dropped it. It just hits the ground a long, long way away, So I want to show you now something. In the video, it didn't hit the ground exactly at the same time as the drop bullet, right? It was pretty close, but I think they said 39 milliseconds, a little under 0.04 seconds. I mean, that's something. 39, I think that's right. And so, what could have caused that difference? Probably not air resistance. Even though there's a lot of air resistance on a bullet, air resistance always acts in the opposite direction of its velocity. And so the bullet is mostly going horizontally, So even though there's a lot of air resistance on it, it's not affecting its fall down very much, The thing that I think probably affected, most likely sort of culprit for why they hit the ground a little bit different times, is just the difficulty of getting that bullet to come out exactly horizontally. So I want to do a calculation now to show like the effect of very small angle differences. How much can these small angle differences affect how long it takes for the thing to hit the ground? And sort of help you wrap your head around this thing that's sort of weird, you know? I mean, it seems strange when you first see it. Okay, so what if the bullet fired, and last time I think we said it was 1 meter off the ground, so let's do that. What if the bullet fired was 0.1 degrees above horizontal? How much would that affect the time to hit the ground? Okay, so this time it's going to be fired, well, again, from a height of 1 meter. But if that's the horizontal, this time it's going to be fired at an angle. Obviously, that's a huge exaggeration. 0.1 degrees is such a small angle. You really can't eyeball that at all. But we're going to say it's fired at an angle of 0.1 degrees, and we're going to say the bullet is going 1,000 meters per second. And so the path is going to be a parabola that starts out with that line tangent to it and follows this path. If it was totally horizontal, the fall time would be 0.455 seconds to hit the ground. Okay, so let's calculate what it is in this case. So the key thing is this is a tiny, tiny angle. All right, so the first thing we have to choose is a time equals 0 instant and a time final instant. What's going to be time equals 0? Yeah, that's the instant that it's fired. And what's going to be time final? Yeah, the instant, right before it hits the ground. And then we have to choose a coordinate system, a location, and an orientation. I'm going to do what I always do, just put it on the ground, underneath where the object is at time equals 0. And now we can figure out what variables we know and what we're trying to calculate. TF, do we know that? What the stopwatch says when it hits the ground? No, that's what we're trying to find. It's free fall, so the acceleration is 9.81 down, or in our coordinate system, 0, negative 9.81. Do we know the position at time equals 0? Yep, and remember that the position vector you can think of as the coordinates of the object, so that's 0 for x, positive 1 for y. Do we know anything about the final position? We don't know how far away it is in x, but we do know that it's 0 for y because it's hitting the ground. And our coordinates, our origin is on the ground. Okay, and now initial velocity. That's where we're going to use this 1,000 and this 0.1 degrees. So this initial velocity is going to be 1,000 times the cosine of 0.1 degrees and the sine of 0.1 degrees. And that is it's 999.998 for the x component. So I'm just going to call that 1,000 for the x component. And the y component is 1.75.
How do we get to 1,000?
This is 1,000 times, you can also, what I wrote like this, you can also write as 1,000 times the cosine, 1,000 times the sine.
I know how we get that 1,000.
How did I get that number? So in my calculator, you basically just type it in like that. So 1,000 times the cosine of 0.1, and that's 999.998. And then for y, 1,000 times the sine of 0.1, 1.75. Every calculator, you enter it a little different. So please come talk to me if you're having trouble getting that answer. It's the most common thing, if you type something like that in and you get the wrong number, the most common problem is that your calculator is in radians instead of degrees. Okay, and do we know V final? No. If you're at a cocktail party, do we know anything about V final? Yes, at a cocktail party, we don't mind, relaxing a little bit and saying like, okay, I'll level with you. We really know that the x component of the velocity is never going to change over the motion. And that's because the only acceleration is in the y direction. But for calculation purposes, you don't want to put that in here. You want to think of that as something that you'd have to calculate. Because if I put pfx in here, a lot of times it would lead me to think that equations will work that won't work. Okay? So you don't want to put that in there. All right, is there an equation that works for TF? Yes, this one should. PFY is equal to PIY plus VIYTF plus 1/2 AYTF squared. Plug in the numbers. 0 is equal to 1 plus 1.75 TF minus 4.905 TF squared. Since this equation has a variable squared and a variable linear and a constant, we have to use the quadratic formula. So here's A, B, and C. And so plug that into the quadratic formula. And you get TF is equal to negative 0.307. Well, we know we don't want any negative times, so that one's out. And then, so the one that we want is 0 point, ready for it? We're comparing to 0.455 seconds. This is 0.664 seconds. Okay, so in the Mythbusters video, they were off by 39 milliseconds. This is off by, you know, I mean, basically 200 milliseconds, okay? So if the angle that they fired that bullet was the problem that caused that difference in times, that angle was off by far less than 1/10 of a degree, you know? So that's how much, when something's moving really fast, like a bullet, that's how much of an effect the just small changes in angle can make. How high do you think the bullet gets? Yeah, it definitely will get, I mean, if you look at this picture, this is exaggerated, you know, but you can see that because it's fired up, it is going to go up a bit higher than it was fired. Let's calculate that. Is there any reason to choose a different time equals 0 instant? No. What about time final? Yeah, this time we have to choose the instant it gets to the highest point. So this is the instant that it reaches the highest point. We don't know time final. We know the acceleration. The initial position is 0, 1. We want PFY. VI is what it was before, 1,000 for X, 1.75 for Y. And since this is the highest point, we know that VFY is equal to 0. And the equation that'll work here is 2A times the quantity PFY, 2AY, sorry, times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. So plug stuff in, you get negative 19.62 times the quantity PFY minus 1 is equal to 0 squared minus 1.75 squared. And so PFY is equal to 1.156 meters. So I don't know. It goes up 16 centimeters higher than it was dropped from. Now I want you to think about one more thing before we leave this. This whole idea was that we did like a 1D problem and a 2D problem. And it turned out that the horizontal motion of the bullet didn't affect its 1D motion up and down, right? That was sort of the idea. So what do you think? So this is a 2D motion now where the bullet is being fired at a little bit of an angle above horizontal. What do you think is a corresponding one-dimensional motion that would hit the ground the same as this? Look at these values we have. Like, what's the thing that makes it take longer in these equations? Well, the answer is in that initial velocity, the y component of the velocity is 1.75 meters per second. And if you shot the one bullet at that angle and took the other one and threw it up into the air with a starting velocity of 1.75 meters per second, okay, but just straight up, it would reach a highest point of 1.156 meters, and then it would start to come down, and those two bullets would hit the ground at the same time. Okay? Any questions about this? Any questions about why we're still talking about this? Okay. So now we'll go on to something else. So now we're going to talk about an intuitive understanding of acceleration in 2 dimensions. This is something that we're going to spend a lot of time on in labs. All right, so in 1D, acceleration isn't as hard to wrap your head around. In 1 dimension, an acceleration means the object is changing speed. You know, it can be speeding up or slowing down, but that's the only thing acceleration can mean. And remember, if the velocity and acceleration are in the same direction, the object is speeding up. And if the velocity and acceleration are in opposite directions, it's slowing down. In 2 dimensions, acceleration can mean 2 different things. The first one is it can mean changing speeds. And what we'll see is whether it's changing speeds is determined by the part of an acceleration vector that's parallel to the velocity. I'm going to call it acceleration parallel. So this is just a part of the acceleration, okay? And if the velocity and the parallel part of the acceleration are in the same direction, do you think, based on 1D, the object is going to be speeding up or slowing down? Speeding up. And if velocity and acceleration parallel are in opposite directions, then it's going to be slowing down. Okay, so in 2D, acceleration can mean that the object's changing speed, but it also can mean that the object is turning. And whether it's turning is determined by the part of the acceleration that's perpendicular to the velocity. So I'm going to call that a perpendicular. There's no turning in 1D because you're just moving along a line, you know? But in 2D, you have to think about that. Objects can be moving in a straight line or turning this way or turning that way. And the only way that you don't have acceleration is in 2D is if the object is moving with a constant speed in a straight line, okay? Then the total acceleration is just the sum of these two parts. Okay, so if you can figure out something about these two parts of the acceleration, it can help you visualize what the total acceleration is. Okay, so to visualize an acceleration vector in 2D, first, draw the object's path in space. Second, draw the velocity vector of the object. That's going to be tangent to the path in the direction of motion. Third, draw the a-parallel vector based on whether the object's speeding up or slowing down. Fourth, draw a perpendicular based on the way the object is turning. And then fifth, the total acceleration is the sum of these two things, a parallel and a perpendicular. Okay, so I'm going to do 3 examples now to show you how this works. I'm going to do one for an object that's, actually I'm going to do 4 examples. I'm going to do one for an object that's moving in a straight line with a constant speed. I'm going to do one for an object that's moving in a straight line with a changing speed. One for an object that's moving with a constant speed but turning. And then finally one that's changing speed and turning. So you can see intuitively how you can use this. Okay, so the first one is an object is just moving along a straight line with a constant speed. Well, I'm going to draw the object's path through the center of the object. So the path looks something like that. Okay. Next, the velocity vector is tangent to that path in the direction of motion. So here's the velocity. Now, is the object speeding up or slowing down? It's constant, so that means that the parallel part of the acceleration is 0. That's right, because so it has a speed, that's the velocity, but acceleration, the parallel part of acceleration only is non-zero if the speed is changing. That's what acceleration does, is tell you how quickly velocity is changing in some way. Okay. Is this turning? No, it's moving along a straight line. So A perpendicular is 0. And so the total acceleration is the sum of these two parts. Whoops. And it's also 0. So this is a case where an object has no acceleration. Okay? Anything moving in a straight line with a constant speed has no acceleration. Any questions about that? Okay, so now let's think about one that's moving in a straight line, but the speed is changing. So let's say that this is moving down the ramp and speeding up. The path of the object going through its center is like that. The velocity vector is tangent to that path. So there's the velocity. Is it speeding up or slowing down? Speeding up, so is A parallel in the same direction as V or the opposite direction? Same, yep. So A parallel is this way. Is it turning? No. So A perpendicular is 0. The total acceleration is the parallel part plus the perpendicular part, and the perpendicular part is 0, which means that the total acceleration is just equal to that parallel part. So that green arrow is the total acceleration in this case. Any questions about that? And well, we're treating this like a two-dimensional problem, but notice it's moving along a straight line. It's really a one-dimensional problem, and so it's acting just like we would expect for a one-dimensional problem. The acceleration is either in the same direction as the velocity or the opposite. Okay, so now let's do one where the speed is constant, but the object's turning. So let's say an object's moving around this circular path. There's the object. Let's say it's going this way. And it's moving with a constant speed. the velocity is tangent to the path, so there's the velocity vector. Is the object changing speed? No, so the A parallel is equal to 0. Is it turning? Yeah, anytime it's not traveling on a straight line, it's turning. So now you have to think, which way is it turning? Like, from the way I have it drawn here, you have to think, is it turning to the left or the right? One way to think about it that always works is imagine fitting a circle into the curve of the path. Then A perpendicular always points toward the center of the circle. Well, this is actually a circle already, so A perpendicular is pointing toward the center of this circle like this. So the total acceleration is A parallel plus A perpendicular. A parallel is equal to 0, so it's just equal to this. So for this object moving around a circular path with a constant speed, the acceleration is toward the center. Okay? And then the last one, the deluxe model with everything going on. So let's imagine a ball rolling down a curved ramp. The object's path is something like this. Okay, so first the velocity is tangent to that path, so the velocity is something like that. Notice that all these vectors, even when the path is curved, the vectors are straight. Vectors are always just arrows. They can't have curves on them. Oh, this is speeding up because it's rolling down. I didn't write that. Since it's speeding up, is A parallel in the same direction or opposite direction of the velocity? Same, yep. So A parallel is going this way. Now think about which way this is turning. Imagine fitting a circle to the curve. That circle would be like this. And so A perpendicular goes toward the center of that circle, so like this. Well, acceleration is equal to A parallel plus A perpendicular. What we have here is we're adding two vectors where we know their directions, but we don't know their magnitudes. And the half of the class that just had lab this morning knows that we can't say everything about what the sum of these two vectors is, but we can say that it's somewhere between these two directions. And so the total acceleration is somewhere in here. Okay? I know this is, you're just seeing it for the first time. It's going to be a little hazy at the start, but we're going to do this a lot this semester. Anybody have any questions about any of those? One more question. So think of an object in projectile motion on the way up. So let's say that the object is traveling in a parabolic path like this, and the object is here. So let's think about the acceleration of this. Well, projectile motion we already know a lot about. What's the direction of the acceleration when something's in projectile motion? Yep, straight down, okay? So with this other analysis where we're going to get this range of directions, our range of directions that we get better includes straight down or something's wrong. Do you understand my reasoning there? So let's think through it and we'll see that we get a range of directions that includes straight down. Like this analysis agrees with what we already know. Okay, so the velocity is tangent to the path. An object that's on the way up in projectile motion, is it speeding up or slowing down? Slowing down. So A parallel is this way, opposite the velocity. If you fit a circle to this curve, it would be on this side. You see that? And so that says that A perpendicular is this way. And so we know that the total acceleration is somewhere in between the two parts of acceleration. And so the acceleration is somewhere in that range. And the real answer is this, which is included in that range. Okay. Well, that's the last thing I'm going to say about 2D kinematics. So now we're going to be getting into 2D kinetics. So who remembers the definition of kinematics? Remember, kinematics is describing motion without causes. So now we're getting into kinetics, where we're going to combine kinematics with the causes. And the causes that we're going to include to start are mass and force. So the first thing I have to do is define mass and force. Eventually, our goal is going to be to come up with the most important equation in this class, which is Newton's second law. And Newton's second law relates acceleration, a kinematic quantity to mass and force. Okay, so that's what we're heading towards. So I'm going to start by defining mass. And you can think of mass as an object's resistance to acceleration. Mass is related to weight, but it's not the same thing. Weight is how hard gravity pulls down on you. Mass is something that doesn't have anything to do with gravity. On the moon, your weight is different than it is on Earth, but your mass is the same on the moon as it is on Earth. For astronauts, like on space stations and stuff, it's a big concern that there aren't the same forces acting on them as there are on Earth, and they can lose bone density and lose muscle mass. And so it's really important to keep track of an astronaut's mass when they're up there. But how do you do that? You can't use a bathroom scale. Their apparent weight is 0, so you can't stand on a scale and measure it. So how do they measure their mass every day? They literally put them in a machine that shakes them back and forth with known forces and measures their acceleration. And if your mass is high, it's more resistant to that acceleration than as your mass goes down. Okay. Okay, so here's here's a football, relating it to football. Okay, so when these two players collide, there's a big difference in mass. And so there's going to be a very small acceleration for the big person and a very large acceleration for the small person. The velocity of the small person is going to change drastically. This is what you see sometimes if the punter has to run with the ball or something. You see a collision like this, and it's always funny to watch. So when they collide, the big player will have a small acceleration. The small player will have a big acceleration. The SI units for mass are kilograms. You might think it would make more sense if it was grams because this has a prefix on it, but kilograms is the SI units. In British or imperial units, you probably also would think that the measure for mass is pounds, but this is where everyone gets thrown off. Pounds is really a measure of force. So when your bathroom scale has a conversion on it, a button you can flip to switch from kilograms to pounds, it's really actually doing the conversion it's based on the fact that it assumes you're going to be on the surface of the earth when you use this scale. And so it knows how much gravity is going to pull on you at the surface of the earth. Okay? But if you use, but it's really measuring force. So if you use a bathroom scale on earth and it says you have a weight of, 200 pounds, and then you use a bathroom scale on the moon and it says you have a weight of, what would that be? 17 pounds or something, Those are both accurate. That is the force that gravity is applying to you in both of those cases. But if you have it on kilogram setting and it says you weigh 80 kilograms, and then you go to the moon and it says you weigh, whatever. I think I did too little, but say 10 kilograms or whatever. That's wrong, but let's say, that actually is incorrect because the scale is measuring your force on the moon, assuming you're on the surface of the earth, and then figuring out what your mass would have to be on the surface of the earth to produce that weight force. It doesn't know that you're on the moon. So anyways, pounds are not a unit of mass, they're a unit of force. One thing to notice about this is that mass is always a positive number. It's not a vector. It's not a vector, so it doesn't have any direction. Also, I'm not going to write this down. We'll talk about this later on. But what this means is, since this is a positive number, what would happen if you multiply the mass of something to a vector? You'd get a vector that's in the same direction because of what multiplication of vectors by numbers does. Okay, so that's going to be an important thing later on. The next thing we have to define is force. And force is a vector. That measures the intensity and direction of a push or pull on an object. The units of force the SI units of force are kilogram meters per second squared. It's a really messy unit. And since it's going to be a really important unit for us, and this is kind of a mouthful to say and deal with, we're going to call this 1 kilogram meter per second squared a Newton. And we'll denote it with a capital N. And the thing I want you to keep in mind about forces, so notice that in this class, there are only two ways forces can arise. So there are only two ways forces can be applied to an object. The first is the weight. So that's the force that gravity applies to the object. And the only other way that force is applied is contact forces. And that's a force applied by contact with another object. Any questions about that? All right, well, next time, here's what we're going to do. I'm going to stop here. But next time, we're going to use these for Newton's second law. This is the most important equation in this class. And Newton's second law says if you add up all the forces on an object, that's called the net force. That's equal to the mass of the object times the acceleration of its center of mass. F equals ma, you've probably heard of that somewhere or other. And so we'll start talking about how to use Newton's second law to figure out forces, to figure out accelerations, that kind of stuff. Anybody have any questions for now? All right, I'm not going to give an assignment for today because you have the test coming up, but I will give an assignment on Thursday, so look for that after the test. Okay, that's all.